So we consider an example of computing the derivative of implicitly defined functions. Okay, so suppose u1 and u2 are functions of x1, x2, x3. Maybe we use y1, y2. Defined implicitly from f1, x1, x2, x3, y1, y2, f2, x1, x2, x3, y1, y2, okay, equals 0. So when this can be true, when we can solve y1, y2 to be a function of x1, x2, x3 from these two equations, the implicit function theorem tells us that if this condition, the Jacobian determinant of f1, f2 with respect to y1, y2 is not 0. If this condition is fulfilled, then we can solve y1, y2 from this system of equation capital F1, capital F2 equals 0. We can solve for y1, y2 using x1, x2, x3. Because if we denote capital F to be F1, F2, okay, and the derivative of capital F with respect to y is precisely the matrix of F1 with respect to y1 and respect to y2 and F2 with respect to y1 and F2 with respect to y2. So this is precisely the determinant of this matrix is precisely the Jacobian determinant of F1, F2 with respect to y1, y2. So if the Jacobian determinant is not 0, then this matrix is invertible. So applying the implicit function theorem, we can solve y for x. We can solve y using the express y in x. That is y is a function of x. So this is the case, y1, y2. Now our problem is having known that y1, y2 can be implicitly defined as a function of x1, x2, x3. How to compute the derivative? To compute, if we want to compute dyi dx2, for example, I is 1, 2. So we simply derivative the equation here. We simply take the derivative of these two equations with respect to x2. Okay, so derivate f1 equal to 0 with respect to x2. We obtained df1 dx2 because df1 dx the first three arguments are independent variables. The first three variables x1, x2, x3 are independent variables. Therefore, the derivative of f1 with respect to x2 has nothing to do with s1 and s3. So we have this term. And then we need to compute the f1 with respect to y1 and then y1 with respect to x2. This is a chain rule plus f1 with respect to y2 and then y2 with respect to x2. So this is 0. Similarly, we take the derivative of the second equation. So we also have df2 dx2 plus df2 dy1 dy1 dx2 plus df2 dy2 dy2 dx2. This is 0. So this is a system of linear equation. Two equations and two unknown. The two unknown is dy1 dx2 and dy2 dx2. So solving this system of equation for dy1 dy2 and dy2 dy2, we can obtain the result. For example, dy1 dx2 is, firstly, using the Clement law, it should be the coefficient, the determinant of the coefficient metric, that is, or maybe it will be more clear to write this in metric form. It will be better to write in metric form. That is dy1 f1 dy1 f dy2 f dy2 f1 dy1 f2 dy2 f2 and dy1 dx2 dy2 dx2. This will be minus df1 dx2 df2 dx2. So using Clement law, you can solve for this. This is simply linear algebra. I will not spend time on this topic. It is very simple. Okay. So now, having studied the inverse function theorem and the implicit function theorem, we will go back to look at the surface in Rn. Surface in Rn. So what's surface? It is reasonable to consider the surface as a subset of Rn, which is locally a graph of some smooth function. So surface in Rn is a subset of Rn, locally a graph. Of a smooth function. A -1 variable function. Okay, so we consider several typical examples of surface. The first example, our capital F is a function in Rn. C1, continuously differentiable, and our capital M is the inverse of 0 under F. We assume that this is not empty. That is, M is the set where F is 0. So this is M. F is 0. Okay? Now we assume that for any x in M, the gradient of F is not 0. Okay? So consider a point. For any point in M, given A in M, suppose A is here, we might assume at this point A, the derivative with respect to xn is not 0. Because the gradient at A is not 0, at least one component of the gradient is not 0. Okay? So without loss of generality, we assume that the last component of the gradient at the point A that is the partial derivative of capital F with respect to xn is not zero. Then by implicit function theorem, following the equation f x1 xm equals 0. Of course, since a belongs to m, means that f a1 am is 0. Okay, so but the partial derivative with respect to xn is not 0, means that from this equation we can obtain the sorry, our dimension is wrong. This should be n. We are in Rn, not Rm. Okay, so now our xn, because the partial derivative with respect to the last variable is not 0, so we can solve for the last variable. Xn is a function of the other argument, x1, xn minus 1. This means a point x1, xn lies in our M if and only if for those points near the point A, in the neighborhood of A. A point x which coordinate x1, xn belongs to this M if and only if xn is phi x1, xn minus 1. That is, this point lies on the surface, on the graph of our function phi. And the phi is a C1 function. Therefore, this means that locally our capital F equal to 0, that is our subset M, is a graph of a function. So the graph, this M, because this is true for every point A in M, so this M is a surface. Okay, and we also know in our previous study that the normal vector of the surface M at the point A is precisely the gradient of capital F at the point A. Okay, so this is a surface and it's a normal vector. Now we consider another example. Suppose U is an open set in Rn-1, and our X is a map from U to Rn. It's a C1 map, continuously differentiable. For any U in this set, we assume that the rank of the derivative of the map X at the point U is n-1. What this means? This derivative, because X is a map from n-1 dimensional open set U to Rn, therefore the derivative is an n by n-1 matrix. The entries of this matrix is dxi duj. Here I is from 1 to n, j from 1 to n-1. Okay, so under this assumption, that is X is smooth, and the rank of this metric, the derivative metric of X at every point U is n-1, then the image of this map is a surface in Rn. Okay, how to get this result? So